My name is Clive Hogan, and I'll be presenting the paper on VEEGAN, reducing mode collapse in GANs using implicit variational learning. Right, so just a quick review of generative adversarial networks. So they've got a generator, takes in noise, and outputs synthetic images. The synthetic images, along with a set of real sample images, are fed into a discriminator, which decides whether each image is real or fake, and the accuracy of its decisions is used to generate a loss function, which feeds back into the learning rate of the generator and the discriminator. So this is just the objective function for a normal GAN. It performs a min-max game with the generator, trying to maximize the value for the discriminator and minimize it for the generator. So mode collapse. So one of the issues that can occur when you're working with GANs is mode collapse, and this occurs when the generator learns to generate samples from only a few modes of the data distribution, but misses others even though they are present in the sample data. Here's an example of what can happen when mode collapse occurs. So the discriminator will sometimes recognize that the generator is only producing images from certain modes and starts disbelieving the samples from those modes more often, which will lower the score that the generator is getting. And that in turn makes the generator switch to another mode, which will temporarily boost its score, but eventually the generator or the discriminator will catch on again, and as a result, instead of additional training steps increasing the accuracy of your generator, it actually just bounces around on what mode your generator is mimicking. All right, so VEEGAN addresses mode collapse through the addition of a reconstructor network that takes in synthetic images and real images and basically reconstructs the noise. So for the synthetic images, the reconstructed noise should match the initial noise that was fed into the generator, and that noise is the difference between that noise and the initial noise is used to generate another loss, which is used to for the learning of the generator and the reconstructor networks. All right, so I'm going to go quickly through a diagram that explains how the reconstructor works. So starting off down here, we've got Z representing the data space of the initial noise. So P0 of Z represents the Gaussian distribution of noise that's used as the input to the generator in a GAN.
And these are the, we'll go back. So those are the data, those are the sample points which were sampled from that noise.
Right. So yeah, this Gaussian curve here is the samples that the noise samples.
Just point those dots. Those are the samples.
These dots.
Okay.
Right. So those will show up a little bit more in the next slide. All right. So this layer X is the data space representing the images that are generated from the GAN, or from the generators. And these green lines represent the action of the generator. Shown here is G gamma taking samples, these samples here, from the noise distribution and generating synthetic images. So P of X here is the actual distribution of the sample images. So you can see here that the generator is only creating images in one of the two modes. So we already know that for this example, the generator is experiencing mode collapse. All right. So this C up here represents the noise data space again, and this is where the reconstructor network comes in. So the reconstructor network, shown here is F theta, takes the images from the data space, both the real ones, which are represented by these purple lines, and the green one, the synthetic ones shown by the green arrows, and maps them back to the noise space up here, which will create these two distributions. So earlier I said that the Reconstructor network had two goals, and I'll discuss them now.
So talk about what is the green one, what is the pink one.
Okay, so here the green one represents the distribution of the noise from the synthetic images after they've gone through the Reconstructor network. The purple one shows the distribution of the noise after its sample images have gone through the Reconstructor network. Right, so the first goal of the Reconstructor network is to approximately invert the generator, which means that the Reconstructor forms an autoencoder with the generator. So this noise is translated into these images, which is translated back into this noise, this green curve should match up with this initial Gaussian noise curve. In this example, it succeeds. The two distributions match up, but if you notice, the purple distribution is significantly different, which brings us to the second goal of the Reconstructor network. So the second goal is to map the real data to a Gaussian curve as well. In this example, which is different than the previous one, it does succeed, but as you can see, it fails on the first goal because this Gaussian distribution doesn't match up with this one down here. This is happening because the network is experiencing mode collapse. The Reconstructor, f theta, is basically expecting data from this entire curve to generate this Gaussian curve, but because it has mode collapse, it's only getting data from over here for the green curve of the synthetic images. Alright, so this is the objective function of the Reconstructor network. So this first term is the autoencoder loss, which basically boils down to minimizing the difference between this initial noise curve and the green noise curve that represents the reconstructed noise from the synthetic images. And then the second term is the cross entropy between once again, the initial noise curve and the reconstructed noise curve generated from the real sample images. So unfortunately, this objective function is hard to compute. So the authors perform several intricate conversions that eventually end up with this function. So these two are basically equivalent, but this one is easier to compute. So KL over here is the Kullback-Leibler divergence, which is also called relative entropy, and it's a measure of how one probability distribution diverges from a second. In this case, it's measuring the difference between the reconstructed noise from the synthetic images and the initial noise. This term here is just...
So let me slow down this, explain a little bit more. So here, so you have two terms, the P0Z, so that's the noise, and then given Z, then it generates the sample, right? So that is the distribution of
the synthetic images.
And then other term?
So this other term is P of X is the sample images, and then given that X, it's generating noise again from the Reconstructor network. And, so the second term is just a measure of entropy over the initial noise. And then the final term is measuring the difference between the initial noise Gaussian, which is this Z, and the reconstructed noise from real images, the real sample images. All right, so next up I'll explain the training cycle for the VEEGAN implementation. So up here we've got, while it's not converged, for each sample in the batch, from the Gaussian distribution of noise, take a sample and store it as ZI. Then this next step, you take your initial noise sample, feed it into the generator, which is marked as Q gamma for this one, and get the image and store that one, store the new synthetic image as XIG. All right. Then you take one of the sample images, store that as XI.
Sample from the real.
Yes, so the real input sample images, you take from that collection, you grab one for the XI sample. All right. In this line, P theta is the reconstructor network, and it's basically just taking the real sample image that you got in the previous step and using it to generate reconstructed noise, and it's storing that as ZIG. All right. So in this next step, it's computing the gradient of W, which is used for the discriminator. So it's in here, it's using a specially trained modified discriminator to estimate the density ratio from the KL term in the previous objective function. And the value for a generated image in the discriminator is this one here. So it takes the sum of the discriminator's results for the generated images for this one, and this one is for the real images. So this step, you're computing the gradient of theta, which is used in the reconstructor network, and basically it's taking the sum of the distances between the original noise Gaussian, which is the sample that you took up here, and the reconstructed noise Gaussian value, which is the sample that you took over here, and basically dividing by the total number of samples to figure out what that value is. In this next step, you're computing the gradient of gamma, which is used in the generator, and basically the first part here is summing the modified discriminator values for the generated images, and then this second component here is summing the distances between the original noise and the reconstructed noise again. So this right here is exactly the same as this one up here. All right, so once you have those values, you're just performing stochastic gradient descent updates for the W, the theta, and the gamma, and that completes the loop for the VEEGAN training, and that just continues onward until it actually converges. All right, so they ran several experiments in the paper. I'll be going over the results of them now. So the first set of experiments they ran were on synthetic datasets. This was one of them. So this is the true data, and then after running the networks on it, so if you look at the GAN, you can see that it's doing what I explained at the beginning. Rather than having subsequent training cycles increase the accuracy, it's actually just bouncing from one to another, and then at the time that they stopped it, it ended at this one here. So for Ollie, what's happening is rather than showing the distinct modes, it's just getting the average of them, which doesn't actually show up in the real data. And then for this particular one, the Unrolled and VEEGAN did about the same, and they both pretty much captured the true data.
In this one, the same example, they do GANs, right? But they don't show the results for GAN.
I think GAN came after this one.
After this or before? Because this was in next in December.
Yeah.
So the interesting thing is that the professor in the GAN is the former advisor of the professor in this one. Chris Russell was student of Phil Tower. So, but I don't know why he didn't put his advisor's paper. Okay, yes, good.
So here are the results for that 2D ring I just showed you. So for modes, it's taking the total number of modes that the network was able to recognize. So once VEEGAN did the best, it recognized all 8 modes. So for high quality samples, the way they're calculating that is that if a sample is within 3 standard deviations of the nearest mode, it marks it as a high quality sample. And once again, VEEGAN did significantly better than these two, but not as well as the normal GAN.
So what does that mean? Like, so
this is
yeah.
So what this is calculating is how many samples were close to the true data samples. And on this one, GAN did very well because, as you can see back here, it just did these, and these are very close to this one mode.
Oh, I see. It's not it's like precision, not ability.
Correct.
We can't capture that and we capture the other ones.
Yes.
Okay, good.
So in addition to the ring, they also did a 2D grid. VEEGAN did decently well on that one. Had significantly more high quality samples than the others. And then they did a 12,000 or 1,200 dimensional synthetic set, and it once again did significantly better than the others for the number of samples that it got and the number of modes it recognized. So the next experiment they ran was on stacked MNIST, which was specifically designed to stacked MNIST was specifically designed to increase the number of discrete modes, and it's just created by taking 3 randomly sampled digits along the red, green, and blue color channels, and it creates 1,000 modes. So, as you can see here, basically, so DCGAN did a few that showed similar to the true data, but most of them are just basically random shapes. Ollie just put out noise on a bunch of them. The same thing happened with Unrolled, but if you look over at VEEGAN, you can see that it did decently well on this data set.
So the idea here is, when you go back, that the GAN should generate these stacked digits, right? So as a 6 and 1.
Yes, so there are 3 digits stacked along the color channels, and then the generator is supposed to regenerate 3 digits stacked by the color channels.
So and that's what they have 3 modes.
So there are 1,000 modes. Yeah, it's every possible combination of 0 to 9.
So in this one, then like 1,000 modes, I see. So which means that any of these digits, I see. So that's, you're looking at 3. Okay, yeah, that's fine. Yeah.
And then the final experiment they ran was on the CIFAR 10 dataset. So basically, they had the real sample images, and for this test they basically found the closest generated image to these real samples, and then that's what shows up here. This first column is DCGAN, next column is Ollie, third column is Unrolled, and then the fourth column is VEEGAN. So this is just another set of that same test, and then so it's kind of hard to qualitatively compare them because of the size, but here are 10 some random VEEGAN generator samples for the CIFAR 10 dataset. And then the results for the stacked MNIST, there were 1,000 modes. None of them came close to actually capturing all the modes, but VEEGAN did do significantly better than the others. And then, so over here, the KL is the Kullback-Leibler divergence, which was the difference between the two distributions. And this one's measuring the difference between the distribution of the real images and the distribution of the images generated by the network. So smaller is better, and once again, VEEGAN had the best. And then, so this is the data from the CIFAR 10 test. So it was inappropriate to assume that each class in CIFAR 10 was composed of a single mode. So what they did instead was they used IVOM, which stands for Inference Via Optimization Metric, which compared the real images from the test set to the nearest generated image and measured the difference between them. The idea behind this measurement is that if there was mode collapse, you'd get some images that were very distant from the nearest generated image. And so then, once again, smaller is better for this one. And it didn't do the best. Unrolled GAN did better than this one on that test.